continue with this transmission line discussion today, this morning, and we should be able to finish this this morning. Okay. Do you have any questions? Okay. Homework 1 is due tomorrow morning. You need to use SPICE and also hyperlinks. So I'm going to introduce hyperlinks, and then if you have not installed SPICE or hyperlinks, then you need to install them. Okay, I will introduce a little bit of SPICE and a little bit of hyperlinks today. Okay. All right. From a digital design point of view, we're interested in square waves. So this afternoon, I'm going to introduce square waves to you. So that's why these examples I'm using is all I use step function. Okay, so that's all we're interested. And of course. And transmission line theory was developed for microwave applications where sinusoidal waveforms are more important than square waves. Okay, but from digital point of view, and actually it's much simpler than because we just have square waves. Okay, so this is what we're interested. Okay, and the most important thing is the reflection coefficient. Okay, when the wave hit a load, this is the load, this is the characteristic impedance of the line. When the wave hit a load, and part of this is going to be reflected. Okay, this is the definition of reflection coefficient, which is basically a percentage of incident wave that's be reflected. Okay, at a load, and turned out that if we know the load impedance and then the characteristic impedance of the line, then we can calculate the reflection coefficient. Okay, if this load impedance is just resistor, then reflection coefficient is a constant, is a real number. Okay, and if the load impedance is not just a pure resistor, and we can use phasor analysis, and we have, and then the reflection coefficient can be a complex number. Okay, and given the reflection coefficient, we can also define transmission coefficient, which is percentage of incident wave that's been transmitted to the load. Okay, which basically means the load voltage here. That's the same definition. Okay, so we know this reflection coefficient, we can represent transmission coefficient by reflection coefficient. Basically, transmission coefficient is 1 plus reflection coefficient. Okay. Right? And then we can also define current reflection and transmission coefficient. Okay. The current reflection coefficient is equal to current voltage reflection coefficient, but the current transmission coefficient is equal to 1 minus current reflection coefficient because the sign convention. Okay, I'm going to skip this. I include this for completion. If you study, if we analyze the sinusoidal waveforms, this is the phasor form. Then we have all these parameters, and but one thing we assume the line is lossless, so that we don't have R and G. There's lossy transmission line representations. So the characteristic impedance is equal to L over C, square root of L over C. Okay, that makes everything very simple. And also the propagation equation is just a pure complex number, which is basically represent the phase of the wave of the propagation. Okay, so there's no loss. You can see that this is just a complex number that represents a phase difference on the line. Okay, so and this is the example we went through yesterday. Okay, you have a step function of 5 volts, and then source impedance of 30 ohms, and then transmission line is represented by its characteristic impedance and also time of flight or delay of the line. Okay. So it's 10 nanosecond delay from this point to this point. The characteristic impedance of the line is 60 ohms. The load resistance is 1,000 ohms. Okay, and then of course what we want to find out is the voltage at this point and also voltage at this point. Okay, To do this, we use a technique which is called the bounce diagram. Okay. And to use the bounce diagram, we need to know the incident wave at this point. As soon as the step function started to go from 0 to 5, there's a voltage here, and at that point, the source does not see this load at all. That's the key point. Okay, and the source will only see a 60 ohm, which is this resistance. Okay, so that the initial voltage at this point can be obtained by the voltage divider between 30 ohms and the 60 ohms. Okay, that's the initial voltage. Okay, that's the instant wave that hit the line. Okay, and that wave will take 10 nanoseconds to reach this point. Okay, once it reaches this point, there's a reflection. Okay, and of course we need to find out the reflection coefficient, and that reflection will take another 10 nanoseconds to return to the source at this point. Once it reaches this point, because the impedance of this source impedance and the line impedance are not matched, so there's reflection as well. Okay, so there's a reflection at the source. There's also reflection at the load. Okay, so we need to understand this. Okay, and even before we do the bounce diagram, it's actually pretty easy to find out the final voltage on the line, because this is a step function. Okay, step function when time goes to infinity is basically it's a DC. It's a 5-volt DC source. Okay, initially there's some transients. Okay, eventually it's going to be just a 5-volt DC. So if you have 5-volt DC here, then the transmission line will disappear. It's just a short circuit. So eventually the voltage on the line will be the same voltage, which basically is obtained by the voltage divider between this 30 ohms and then 1000 ohms. Okay, so that's how it's a good way. You always have to have some kind of in English it's called gut feeling. Okay. Okay, or intuition about the problem, right? And nowadays, more and more, we rely on computers to obtain solutions, right? Computer simulation and MATLAB, matrix solution, and so on. That's okay. But then, why do we need us? Why do we need engineers? Okay, we need engineers because the computers do not have gut feeling or intuition, but we do. Okay, so you should know before you solve a problem, no matter what problem you have, you should know but basically where the solution is. Okay, or in American culture, it's called a ballpark values. Okay, at this point there's reflection because of the load mismatch, and then when the reflection comes back here, there's another reflection. So the reflection coefficient at the load is 0.89. Reflection coefficient at the source is negative 1/3. Okay, so once you obtain this bounce diagram, then you can find the timing waveform at any given point. For example, if you want to find the middle here at 5 nanoseconds, so the middle of the line, you basically just draw the line and then add all the voltages and at the proper time, so you can find the timing waveform of the voltage at this point. This is distance, right? At any given distance, you basically just need to add all the voltages on this at that point to find the actual values of timing waveform. Okay, and this is a simulation. Okay, and by using SPICE. Okay, so and of course this manual solution is not a very efficient solution. Okay, we use manual solution not because we need to solve a problem, but we need to understand the problem. The bounce diagram is the easiest way for us to understand what's going on. Okay, but once we understand this, we should use computer software or hardware as much as possible. As much as possible, we should not use manual solutions. Okay, as I said, for any subject, with the three aspects: concepts, models, and tools. Okay, manual solution like the bounce diagrams is one of the tools that we can use to solve very simple problems. But once we know how to do this, we should use the software as much as possible. Okay, this is a SPICE simulation. It's a bit hard to read. Okay, and you can see that, and it reaches a steady state here, and then there's oscillation. That's called ringing. Okay, we can actually display values, voltage values at some of these points. Let me show you how to do this. You can go to trace and then cursor and then say display and then go to plot, labels, and then mark. Okay, and then you go to next location and go to plot, mark. So this will give you, oh wow, you can't see this at all. Okay, it's right here, the values are there. Okay, so if you do that, okay, once you get obtain a simulation waveform, you should display the values, voltage values, for each of these using display marker and then display values, so that your plot will have not only the waveform and also the voltage values. So you can compare this against your manual solution. Okay, and as you solve the homework problem, you should do the same. Okay. Any question? Okay. So if you don't have a transmission line component, okay, you know, SPICE, there's two things you need to do to do a SPICE simulation. You need a symbol, which basically is just a schematic symbol that doesn't have any underlying SPICE circuit. You also need a SPICE model for that symbol, so you can do simulation, circuit simulation of that symbol. So, and even if you have a symbol, transmission line symbol, if you don't have an underlying SPICE circuit, and then the SPICE simulation will not be able to generate the waveform. Okay, so if you don't have the symbols, and then I believe I've given you some the class directory from last year. There should be a circuit examples. I can give you this example so you can just have the circuit transmission line circuit symbol there. Okay. All right. That's the first one. Okay. So we can do manual solution. We can do SPICE simulation. All right. Any question? Okay. All right. So this is a circuit. Again, I have 5 volts here. There's a 50 ohm source resistance, and then the line resistance is 150 ohms, and with another 150 ohms. This line is 20 nanoseconds long, and this line is 10 nanoseconds long. Okay. Then the end load is 450 ohms. Okay. So what we want to find out is the voltage at this point. Okay. And then we want to sketch the total voltage from 0 to 100 nanoseconds. Okay, basically the transmission line total transmission length is 30 nanoseconds long. So basically this is about 3 times longer than the transmission line delay time. Okay, so that's this problem. All right, and I've given you this plot for the bounce diagram, also this grid sheet for the timing diagram. So you can use this. This is the distance, and this is time. Okay, distance and time, and so you can use this grid sheet to help you. Okay, and since I don't have a projector, I won't be able to, unless I use, no, I won't be able to. I should be able to use this whiteboard, but this is it's too high. I won't be able to reach that. So, okay. So let me just draw a simple bounce diagram sketch here. Okay. Let's see. We have 30. So this is 30 nanoseconds. This is distance. Okay. Then we go all the way to 100. So I need to divide this into 10 pieces more or less. Okay. So this is 10 nanoseconds, 20, and so on. Okay. Now what we need to do is to find all the reflection coefficients. Okay. So the reflection coefficient at the source, okay, which is the gamma source, okay, is 50 ohm minus 150 divided by 200, which is negative 1.5. Right? That's this. Okay. And then the reflection coefficient at the load is 450 minus 130 divided by 600. Okay. So the load reflection coefficient is 450 minus 150 divided by 600. Okay. So it's 1.5. It's positive 1.5. Okay. So those are reflection coefficients. Okay. And what is the initial wave? How large is the initial wave? What's the value of initial wave? Which is right here, right? Okay. So even if we don't know the values, we know what's going on physically, right? So physically, you can see that the wave should hit the load, final load, at 30 nanoseconds, okay, and then it's going to be reflected back at 60 nanoseconds, right, and then it's going to go back and hit the load again at 90 nanoseconds, right? So this is the wave bounces back and forth, okay. All right. So what is the initial wave? Someone tell me the initial wave, initial voltage. The step function is a 5-volt step function. Okay, so the source is a 5-volt step function. Okay, it's right here. That's a SPICE function there. It's 5 volt, and it has rise time, fall time, and then okay, this is a square wave generation. Okay, it has a rise time TR. TR is rise time, TF is fall time. You can actually generate a square wave with this source, okay? And PW is pulse width, okay? And PER is period, okay? And then TD is the delay of this function, okay? TD is delay. So right now, all of them are 0. So you basically have a pure mathematical math step. Okay, so there's no delay anywhere. Okay, so actually you can use this function to generate square wave. Okay, so to generate square wave, you have rise time, fall time. Okay, then you can generate. You have a pulse width. Okay, and then you can generate period. So this way you can actually generate square wave. Okay, and so that's this source. Okay, again, if you after you install your software, and if your software does not have this source, this is a SPICE. SPICE. There's a symbol again. There's a symbol. There's a SPICE circuit underneath that symbol. So if you don't have that symbol, you can just use my example circuit. You can just paste and copy. You should be able to use this source. Okay. If you can find the source in your installation of the SPICE, then it's okay. You should be able to use it. Okay. Because the only thing I want to do is to generate a step function. Okay. So that's why I made the pulse width and period the same. Right. If the pulse width and period are the same, I have only a step function. I don't have square wave. Okay. So that's why there's a step function here. Okay. And also the simulation, when you simulate, simulation time interval should be less than 100 nanoseconds. Because if it's longer than 100 nanosecond, and then you may not, and then this will become just a pulse. Okay. Because after 100 nanoseconds, this pulse will become 0. Okay. So then if your simulation is longer than 100 nanoseconds, then you're going to see a pulse instead of a step. Okay. All right. So that's the simulation. All right. Any question?
So the same thing may happen in the first example.
Yeah, the same thing will happen in the first example, because again, that's right. There's the same source here. So if your simulation is, that's why you see the simulation stopped at 80 nanoseconds only. So the step is still a step function. But if I do a simulation, if the simulation is longer than 100 nanoseconds, okay, then we're going to see something strange. Let me show you with this example. Okay, if I go to SPICE, edit simulation settings, this is the simulation time. Okay. So if I make it 200 nanoseconds, for example, and if I do a simulation again, the funny thing is sometimes I cannot see this probe is not added correctly. Okay, this is the voltage probe. Somehow I can add it, sometimes I cannot add it. Okay, let me close this. Let me try again. Okay, this is voltage level probe. Okay, it looks fine, but we'll see. No. Okay, so what I do then is to go to trees, add trees, and then add the trees manually. Well, that's okay actually. It didn't change that much. It looks fine. Okay, but the simulation is a little bit longer. You can see, but it seems like it did not change that much. Okay, seems to be all right. All right, but if I change this pulse width, let's say I make it 50. Okay, and now I'm going to have a square wave. Again, I need to go and add trees. There. You can't see it because, let me make this a little bit thicker. There. You can see the simulation is so funny now because the period, no, the pulse width now is 50, nanosecond, and then the period is 100, so you have a square wave. Okay, now you do have a square wave here. That's why the simulation result is very funny.